Okay, let's have a look at the NCEA question 2 now, and I actually think that this is probably easier than the first question that we looked at, even though this one's worth excellence. So this time we've got Sarah again, popular name that. She's standing on the end of a diving board, and her mass this time is 50 kilograms. Remember, we can use our trusty formula, weight force is mass times gravity, to turn a mass into a force. So let's do that now. Mass is 50 kilograms, weight force 50 times 9.8, and that gives us 490 newtons. Okay, now when Sarah is standing on the end of the diving board, it's sagging 5 centimeters or 0.05 of a meter. So that's our X. X is 0.050 of a meter. And the first thing that we have to do in part C is calculate the spring constant. So that's actually going to be nice and easy now that we've got a weight force and we've got an extension. Remember, spring constant is always positive, so we can ignore the negative in the formula. Ignore the negative because K is always positive. So we've got F equals Kx. Our weight force is 490. K is what we're trying to work out, and we multiply that by 0.050. Okay, and in the brain box off to the side, we're going to divide both sides by 0.05. That'll give us 490, divided by 0.050 gives us K, and I think if you work that out, it comes out at 9,800 newtons per metre. Okay, that's the first part done. And then in part D, we need to calculate Sarah's speed when she lands on the board. So she does a jump up, and as she lands, she depresses the board by a further 20 centimetres. So the trick here is knowing that the total extension of the board is the 20 centimetres when she lands on it after jumping, plus the 5 centimetres when she's just standing still on it. So in D here, our extension is 0.25 of a metre. That's where your trick is there. And we know our spring constant is 9,800 newtons per metre because we've just worked that out there. And to calculate the speed, I think the first thing we need to know is the amount of elastic potential energy, because I think we assume here that all of the elastic potential energy gets converted into kinetic energy. So all of the elastic potential energy that's in the board as she goes down gets converted into kinetic energy, which we can use to calculate her final velocity. So elastic potential energy is 1/2 times K times x squared, so we can work that out. We get 1/2 times 9,800 times 0.25 squared, and that gives us 306.25 joules. So that's the elastic potential energy, and all of this gets transformed to EK. So all of that 306.25 joules is then equal to 1/2 times mass times velocity squared. Okay, so I'll put my brain boxes over to the side here. The first thing we're going to do is multiply both sides by 2, and that will give us 612.5. Here's mass times velocity squared. That is a V, sorry. And so is that. And then I'm going to divide by Sarah's mass, which is the 50, 612.5 divided by 50 gives us V squared. And then the next thing I'm going to do is take the square root of both sides. So if I take the square root of 602.5 divided by 50, you can put that all into your calculator in one go as long as you use the brackets. V equals, should get 3. Oh whoops, let's move the book up so you can see, 3.5 meters per second. Okay, so there's quite a bit of work in that question, and I guess it's excellence because you have to make the assumption that all of the elastic potential energy is converted into kinetic energy. That's your trick there. That's the conservation of energy physics principle. Good luck, girls, working your way through that.